Welcome back to Calculus 2. In this lecture, we're going to introduce two comparison tests for infinite series, one of which is very similar to the comparison test for improper integrals. All right, so before we get started with our current topic, comparison tests for infinite series, think back to earlier in the course when we introduced the comparison test for improper integrals. So the improper integral comparison test basically had two improper integrals, one less than the other, one graph was below the other, and we could reach some conclusions based off that. Roughly speaking, if the bigger improper integral converges, then the smaller improper integral has to converge. If the smaller improper integral diverges, the bigger improper integral has to diverge. All right, now we're going to get a similar version for this, but instead of dealing with improper integrals, we'll have comparisons of two infinite series. One infinite series that is less than the other, where the terms here a sub n are less than another set of terms b sub n. Now this version is very similar to the comparison test for improper integrals. This one is going to be called the direct comparison test. And what we're going to see within this lecture is there are two different comparison tests. The first one is called the direct comparison test, and then the second one later in this lecture is called the limit comparison test. So let's get to the first one, the direct comparison test. All right, this one is almost identical to the comparison test for improper integrals. There's some assumptions here that we just have to be clear on. First assumption is we have terms of two infinite series, a sub n and b sub n, that are non-negative. So we can't have any negative values in any of the terms a sub n or b sub n. All right, and the other assumption is if the terms a sub n are less than or equal to another set of terms coming from b sub n, another separate general nth term formula. All right, so it starts off the same. We have one infinite series that is less than or equal to another one. We reach two similar conclusions. If the bigger infinite series involving the terms b sub n converges, then no surprise, the smaller infinite series involving terms from a sub n converges as well. And similarly, the second conclusion is if the smaller infinite series involving the terms a sub n diverges, then the bigger infinite series involving terms b sub n diverges as well. And these are pretty much the same two conclusions from the comparison test for improper integrals. Informally, what this says is if the bigger infinite series converges, the smaller infinite series has to converge. If the smaller infinite series diverges, the bigger infinite series has to diverge. All right, for our purposes, there's going to be some useful infinite series to do the comparison with. Two infinite series that have very clear convergence and divergence criterion, which are the geometric series and the p series. Now, in order to apply the direct comparison test, you need to have some idea if the given infinite series you're working with converges or diverges. So if you think your infinite series converges, you would want to find a bigger infinite series that you know for sure converges. If you think your given infinite series diverges, you would want to look for a smaller infinite series that you know for sure diverges. Now, how do you get that idea first if your infinite series converges or diverges? Well, we're going to use what's called a large N estimation. So let's take a look at a general term here, a sub n defined as n divided by n cubed plus 1. And if we take a look at this expression and think, what does this behave like when the value of n becomes very big, think for the moment, let's say n in this expression is 1 million. In your denominator, you have 1 million cubed, and then you add 1 to that. That addition of 1 is insignificant compared to a million cubed. So for this expression, we can neglect that small part in the denominator, the plus 1. 1 is very small compared to n cubed when n is very large. And what we get here is this large n estimation. We say that this expression, n divided by n cubed plus 1, is approximately equal to n divided by n cubed. Again, the plus 1 is small in comparison to n cubed when n is big. And that expression, n divided by n cubed, just simplifies to 1 over n squared. So our general term here, a sub n, for large n values is basically similar and comparable to 1 over n squared. 1 over n squared would be what we call here the large n estimation of our general nth term. All right, and a third and final useful thing to keep in mind is how you can find a bigger or smaller expression or term. To get a bigger fraction, you can make the denominator smaller. To get a smaller fraction, make the denominator bigger. So it's this inverse relationship. All right, let's go ahead and get to some examples on applying the direct comparison test. We're going to take a look at 5 of them. We'll go through the first one, part A, together, and then I'll give you everyone an attempt at parts B, C, D, and E after we go through part A. All right, let's start with part A. The nth term is 1 over n cubed plus 1. We're going to try to determine first if we think this converges or diverges. And that's where we can perform a large n estimation. So when the values of n become very large, our nth term behaves like 1 over n cubed. Again, that plus 1, we can forget about it. It's insignificant compared to n cubed. And our large n estimation term here, that is basically the term for a convergent p-series in the case where the power p is 3. Now, what this suggests is our term a sub n behaves for large values of n like a convergent p-series term. So this suggests that our infinite series converges. It doesn't prove that it converges, but it guides us through the problem. Since we suspect our infinite series converges, we would want to look for a bigger infinite series to apply the conclusive part of the direct comparison test. All right, now fortunately this one is pretty simple. We can get a bigger term by making our denominator smaller. We can make this denominator of 1 divided by n cubed plus 1 smaller by subtracting 1 from that denominator, or getting rid of that plus 1. This now gives us the bigger fraction, 1 divided by n cubed, and that is a convergent p-series term, as we mentioned above. So what we find here is that our bigger infinite series converges. It's a convergent p-series, which then means our smaller infinite series, the one that we're given, has to converge as well. All right, at this point, pause the video and give yourself enough time to work through the remaining parts, B, C, D, and E. We'll go through them in a few minutes. Let's go through part B. All right, to get an idea first, if we think our infinite series converges or diverges, let's perform a large n estimation. Again, this one is very similar to part A. We have that plus 1 in the denominator. And when n becomes very large, 3 to the n is much bigger than 1. So we can get rid of that plus 1 in the denominator, and we get as a large n estimation term 2 to the n divided by 3 to the n. If you perform some basic exponent simplifications here, you can rewrite that as the fraction 2/3 raised to the nth power. And what this allows us to conclude is we now have a number raised to an nth power. That's the general form for the term of a geometric series. The ratio here, the number r, is 2/3, which is less than 1, which suggests our infinite series seems to converge. All right, since we think our infinite series converges, we would want to look for a bigger infinite series that we know for sure converges. And as it turns out here, we can use the same large n estimation for the bigger term. We can take our term, 2 to the n divided by 3 to the n plus 1, and get a bigger fraction by making our denominator smaller. Again, we're making our denominator smaller here by getting rid of that plus 1. Okay, and what we're comparing with for the bigger infinite series term, 2/3 to the nth power, that is a term for a convergent geometric series. And since here the bigger infinite series converges, our smaller infinite series has to converge as well by the first part of the direct comparison test. Let's move on to part C. All right, this one's a little trickier, but I wanted to include it for a variety of examples. Here, the nth term is 1 divided by natural log of n. And it's worth pointing out here, notice the infinite series starts with the index value 2. We can't start our index here with 1, since natural log of 1 equals 0. And that would give us here, when n equals 1, division by 0. So a sub 1, our first term, would be undefined. So we avoid that possibility and start our infinite series here with n equals 2. Now this one's a little bit trickier, particularly because natural logs are not probably as comfortable for you to work with. Well, let's point out an important feature for them. Natural log of x, or in this case, natural log of n, it does increase, but very slowly. If you take a look at that graph, it's not drawn to scale. It never levels off, but it increases very, very slowly. Okay, what we're going to notice first is natural log of n is less than n. Okay? How we can rewrite this expression to make it look like our nth term, 1 over natural log of n. Let's go ahead and cross divide. So if we divide n and divide natural log of n to the other side, switching them there, we get this inequality. 1 over n is less than 1 over natural log of n. Now, how does this help us? Well, the smaller term, 1 over n, that is the term for a divergent harmonic series. Remember, for the harmonic series, the general term was 1 over n, and that's exactly what we have here. So what we have is now a smaller infinite series, the infinite series for 1 over n, where n starts with 2. Usually for the harmonic series, the starting index is 1, but the index value doesn't matter for convergence or divergence for the starting value. So our smaller infinite series here, the harmonic series, is divergent, which then means that the bigger infinite series, our infinite series with term 1 over natural log of n, has to diverge as well. Let's move on to part D. Again, we're going to try to determine if we think our infinite series converges or diverges. Again, we'll start with a large n estimation. All right, and again, the plus 1 is insignificant when compared to square root of n for large values of n. All right, we can rewrite our large n estimation term here as 1 divided by n to the 1/2 power. And we might recall when you have 1 over n to a power, that is the form for the term of a p-series. And in this case, the p-value is 1/2. That would put this into the divergent case for the p-series. Recall when the power is less than or equal to 1, the p-series diverges. Now, what does this large n estimation term suggest for us? It suggests that our infinite series behaves like a divergent p-series. So what we would want to look for, if we think our infinite series diverges, we would want to look for a smaller infinite series that we know for sure diverges. All right, now this one's a little trickier. If you were to get rid of the plus 1, that makes your denominator smaller. And what you get, if you make your denominator smaller there by getting rid of the plus 1, is you get a bigger term, 1 divided by square root of n. Now this actually falls into the inconclusive part of the comparison test, or direct comparison test, where if the bigger infinite series diverges, that says nothing about the smaller infinite series. So we get an inconclusive comparison here. Now this one's a little trickier. We have to get a little creative. And what we can do for our nth term, 1 divided by square root of n plus 1, is we're going to make our denominator bigger by replacing the 1 with square root of n. Okay, and what that does is now gives us a term in the correct direction. We now get something smaller. Square root of n is bigger than 1. So what we get is an expression here where the denominator has become bigger. Now the benefit of doing this is that you can combine those two square roots of n together and write that as 2 square root of n in your denominator. All right, and that basically gives us now a conclusive comparison. We can compare our infinite series with the smaller infinite series, 1 divided by 2 square root of n. At factor of 2, you could pull that out in front of the summation sign, since that kind of works like an integral sign. Remember, you can pull constants out in front of integrals. Here, for some properties of an infinite series, you can pull constant factors in front of the infinite series summation sign. And what you're left with there for the smaller infinite series is the term 1 over square root of n, which you could rewrite as 1 divided by n to the 1/2 power. So our smaller infinite series here is a divergent p-series where the power p is 1/2. And if we apply the direct comparison test, here the smaller infinite series diverges, which means our bigger infinite series has to also diverge. All right, let's take a look at our final example for the direct comparison test, part E. Here the nth term is 1 divided by the square root of n cubed plus 1. And if we perform a large n estimation, we find that our nth term for the expression when values of n become very large behaves like 1 over the square root of n cubed, which you could rewrite that, think of the square root as a 1/2 power. You could rewrite that as 1 divided by n to the 3/2 power. And the benefit of noticing this large n estimation term, we have now the form for a p-series term, 1 over n to a power, and this would fall into the convergent case of the p-series, where the power p 3/2 is bigger than 1. So what this suggests is our infinite series seems to be convergent, so we would want to look for a bigger infinite series that converges. And as before in previous examples, we can get something bigger by making our denominator smaller, get rid of the +1, and what we find here is a comparison for the bigger p series, where p is 3/2. So we can conclude here is the bigger infinite series converges, our smaller infinite series has to converge as well. All right, these were all examples on the direct comparison test. One of the drawbacks of the direct comparison test is you have to know or have an idea if your infinite series converges or diverges to guide you through looking for something bigger or smaller to compare with. The other drawback of the direct comparison test is it's not at all obvious sometimes how to find the comparison infinite series, the bigger or smaller term. And this is one of the benefits of the next test we'll get to, called the limit comparison test. It takes some of the thinking out of this for having to determine if yours converges or diverges, and takes the thinking out for how to find the comparison infinite series. All right, let's start with an example just so we can have an idea why you would want another test. Let's say we have an infinite series here where the term is n squared divided by n to the 4th minus 1. And notice the starting index here starts with n equals 2. All right, now if we perform a large N estimation to get an idea if we think this converges or diverges, we can notice the -1. That's small compared to n to the 4th when n becomes very large. So for large values of n, our term here behaves like 1 over n squared. The n squared divided by n to the 4th, that just reduces to 1 over n squared. Now this suggests that our infinite series converges, since 1 over n squared is the term for a convergent p series. And let's see what we can determine by maybe applying the direct comparison test. All right, seems convergent, so we want to look for something bigger. But the problem here is if we try to find a bigger infinite series, notice we have -1 in the denominator rather than +1 like we've seen in some previous examples. Now, if we were to get rid of the -1, what we're really be doing is adding an additional +1 in that denominator. And when you add +1, you actually make your denominator bigger. And if you make your denominator bigger, you get a fraction that is smaller. So what we find here is we do get a comparison with 1 over n squared, but it's in the wrong direction. If we were applying the direct comparison test, would need a bigger infinite series that converges to get a conclusive comparison. And here, 1 over n squared is the term for a convergent p series, but the comparison is in the wrong direction. If the smaller infinite series converges, anything can happen for the bigger infinite series. So how do we recover from this? Well, this one's probably a little tricky to apply the direct comparison test to. Fortunately, we can apply this new test called the limit comparison test. All right, so we have our statement here for the limit comparison test. Make sure you're comfortable with the terms. So we have the direct comparison test. Sometimes that's just referred to as the comparison test for infinite series. And we now have this new one referred to as the limit comparison test. As you can see in the statement here, there is a limit involved in the statement of the theorem. All right, it has the same conditions or assumptions as the direct comparison test. The terms a sub n and b sub n both have to be non-negative. All right, and what we look at coming from the name of the limit comparison test is we look at the limit of a sub n divided by b sub n. Why we're looking at that is it basically says something about the terms a sub n and b sub n growing or getting smaller, decreasing, kind of at the same rate. So what the theorem states here, or the test, is if this limit of a sub n divided by b sub n, as n goes to infinity, if that equals some limit value, L, that isn't 0, and this suggests, again, intuitively or informally, that a sub n and b sub n kind of grow at the same rate. If this ratio of a sub n divided by b sub n, as n goes to infinity, if that equals some limit L, then either both infinite series converge or both infinite series diverge. All right, let's go ahead and apply this. One of the main benefits of the limit comparison test is what we did with our large N estimation. That is usually going to be our comparison term when applying the limit comparison test. So we can kind of actually calculate pretty effortlessly what infinite series we're going to compare with for the limit comparison test. It takes all the inequality part out of this, like we had to deal with the direct comparison test. All right, let's go ahead and apply this to a few examples. This one is maybe a little trickier since it involves a lot of ideas involving limits that might have been forgotten as you would have first learned them in your Calc 1 class. So just keep in mind some really nice results on limits, particularly L'Hopital's rule. So we'll go through part A together, and then I'll give everyone an attempt at part B here. All right, our infinite series is for the term a sub n, which is n squared divided by n to the fourth minus 1. If we perform a large N estimation, we find our infinite series behaves like 1 over n squared for large values of n. This large N estimation term, we're going to take that to be the term b sub n that will apply with the limit comparison test. And the nice thing about 1 over n squared, that is a term for a convergent p-series where the power 2 is bigger than 1. So this would be a convergent p-series rather than one that's divergent when the powers are less than or equal to 1. All right, what we have to look at for the limit comparison test is the limit of a sub n divided by b sub n. All right, just recall some basic algebra. Here, a sub n and b sub n are both fractions. So when we perform this division here, a sub n divided by b sub n, we're dividing fractions. We can easily simplify that by multiplying by the reciprocal. So the 1 divided by n squared reciprocates to multiplication by n squared divided by 1. And if you simplify that, multiply those numerators, you get this as coming out to be n to the fourth divided by n to the fourth minus 1. That's the expression that we're going to evaluate the limit of as n approaches infinity. All right, so if we take the limit of that expression, a sub n divided by b sub n, you might notice some basic results here. Like going back to your maybe pre-calc course, here the powers of n are equal, so the limit should be the ratio of the leading coefficients from the expression in the numerator and the expression in the denominator. Here, the leading coefficients of n to the fourth are both 1. So we get as our limit 1 over 1, which is 1. The other way to see this is, notice this gives you an indeterminate form of the type infinity divided by infinity. Since n is approaching infinity, n to the fourth and n to the fourth minus 1 both get bigger. You could apply, since we have an indeterminate form here, you could apply L'Hopital's rule. And if you apply L'Hopital's rule, you'll find you still get a limit here of 1. Now, what does this tell us? We have a limit here that is non-zero. That means both series do the same thing, either both converge or both diverge. And since our comparison term, B sub n, was that of a convergent P series, both series here have to converge. So we find our infinite series with term n squared divided by n to the fourth minus 1, that has to converge by the limit comparison test. All right, at this point, pause the video and give yourself an attempt at part B. This one was one that we saw back in example 1, and we found in example 1, the infinite series here in part B, this actually diverges. So when you apply now the limit comparison test to part B, make sure that you get the same result. You find that this infinite series diverges by applying the limit comparison test. We'll go through that in a few minutes. Pause the video and give yourself an attempt. All right, let's wrap up with part B here. Again, we would want to have a term to compare with, a B sub n. So we can find that by doing a large N estimation. That's again one of the benefits of the limit comparison test. Usually you can calculate by a large N estimation what infinite series term B sub n you would want to compare with. We find here our B sub n is 1 over the square root of n, or 1 divided by n to the 1/2, which is the term for a divergent P series. All right, now if we get a limit here that is non-zero, this would say both infinite series then have to diverge by the limit comparison test. We need to calculate that limit of A sub n divided by B sub n. Same thing as we saw in the previous example, 2a. We're dividing fractions, so you can multiply by the reciprocal, and you get this expression square root of n divided by square root of n plus 1. When we take a limit for that expression, as n approaches infinity, it's very similar to what we saw in part A. In part A, we had n to the fourth divided by n to the fourth minus 1. There, the powers of n were equal, and we have the same thing here. Now we have fractions 1/2 for the powers of n. The powers are equal, so the limit here as n goes to infinity should again be the ratio of the leading coefficients. So again, we find 1 divided by 1, our limit here would be 1. This one is also an example that you can apply L'Hopital's rule to. You have an indeterminate form of type infinity over infinity, and if you apply L'Hopital's rule, you should also find you get a limit here of 1. Since this limit is non-zero, that means both infinite series have to do the same thing, both converge or both diverge. And since our comparison infinite series, the infinite series involving B sub n, diverges, our infinite series diverges as well by the limit comparison test. And if you think back to example 1D, that was exactly the same conclusion we reached. In example 1, we applied the direct comparison test. Here, we're applying the limit comparison test. So when you're going through examples in the homework, Try to apply, where possible, both tests to as many examples as possible. That way you get a nice set of examples to build up your intuition for when you would want to apply one test over the other.